Our speaker today is Mutasim Mim, and he'll be talking about Clique complexes of strongly regular graphs. Welcome, Mutasim. The floor is yours.
Thank you for the invitation, and thank you for coming to my talk. So this work was mostly done with my previous advisor at University of Delaware, and we had a couple more kind of collaborators. Krystal Guo is at University of Amsterdam, and there was another student, Chunxu Ji, who worked on this project before I even joined. I think he's at some California State University at this time. This work can be broadly characterized as a slight generalization of spectral graph theory techniques to capture essentially higher order incidence structure. So in spectral graph theory, we basically study how vertices are included in edges. So this work is about how edges are included in triangles, triangles are included in K-force in the graph, etc. So generalization in that direction. So my goal is to kind of give you a few quick definitions. And then once I have enough to describe the main object of study, I'll give you some mathematical motivation as to why we got interested to study this in the first place. And then I'll basically give you two different kinds of results we found. And I'll try not to prove many things, but I think there's at least one or two proofs just to demonstrate how these proofs look like, essentially. So for us, a simple shell complex is an abstract simple shell complex. We have a finite ground set. We usually never care about the infinite ones, but many of the results easily generalize to infinite cases. But for us today, the ground set is finite, and we have a collection of subsets on that set that is closed under taking subsets. So if a set is in your collection, any subset of that set is also in your collection. So for example, here's a very simple example. Like let's say the ground set is 1, 2, 3, 4, and the subsets are the empty set, the singletons 1, 2, and 3, and a pair 1, 2. And it's easily checked that it's actually a simple shell complex. Oops, let me just get to the correct zoom. This should work. Okay. And the dimension of a simple shell complex is just, the sets in your collection, they're called faces, and the dimension is defined to be the size of the largest set in your collection minus 1. And we also kind of can create this poset by inclusion of all the faces you have in your collection. And at level I, when I say level I mean all faces of like basically dimension I, so size I plus 1. So we denote those by x sub I. Okay, and our primary interest are the simple shell complexes that can be obtained from graphs. And for us, graphs mean simple graphs, no multi-edges and no loops, and undirected. So the first kind of simple shell complex you can create out of a graph is a Clique complex. So your ground set would be the vertex set of the graph, and the subsets in your collection would be just sets of vertices that form a clique in your graph. And it's easily seen to be closed under taking subsets. And you can look at the Clique complex of the complement of the graph, which we call the independent complex. So basically, collection of vertices such that no pair of the vertices is adjacent to each other. And also, we have this matching complex, which is basically the independent complex of the line graph of the graph that we start with, meaning it's just the sets are just collections of edges such that no pair of the edges share a vertex. And we are primarily interested in the Clique complex of the graphs in this talk. Here's an example. So this is the graph I have on the left side. So it's the graph on 4 vertices and 5 edges. And basically, it has 2 triangles. And we can list the various simplices in that graph on the right-hand side. So basically, we have the empty set, 4 singletons for 4 vertices, 5 pairs for the 5 edges, and 2 triangles. And those lines basically like show inclusion. Uh, and so for us, we are going to assume a kind of global ordering on the set on the elements of the ground set. So usually, if there's no confusion, we can just assume that the ground set is always the set of symbols from 1 through n. And we're going to be looking at eigenvalues of certain operators that we're going to define in a bit. And I should note here that this ordering, even though the matrices that we're going to talk about depend on these ordering, the eigenvalues do not. So yeah, so the eigenvalues are kind of independent of what ordering you choose. So we can choose whatever ordering is convenient. And so if you have an I face and an I plus 1 face, then we can define this kind of sign notation that I'm denoting with these colon and brackets, f over k. So it's only defined when the... Yes.
What is K?
So k is an I face, f is an I plus 1 face. So just 2 sets in my collection.
Mutasim, if
Yes.
I may interrupt, I
Sure.
think one of the Zoom members should be close his window.
We can decide it here, no worries.
Yes, thank
Okay, no worries. Yeah, feel free to interrupt me. Yes. Can we move on? Any other questions? Okay. Okay. So basically, this notation that I'm defining is only non-zero when the k face, sorry, the f face can be obtained by adding 1 extra element to the k face. And any other cases, it's just going to be 0. And when it is non-zero, it's either +1 or -1 based on this sign notation. So yeah, so basically this is a kind of one way of saying, okay, is this face contained in that other face or not? And if it's not, then it's definitely 0. And if it is contained, it's either +1 or -1 based on this ordering we have defined previously. And once you have this notation, you can define this co-boundary operator, which is very similar to the co-boundary operator we have in algebraic topology. But for us, our complexes are defined combinatorially, so there's not necessarily any topological space associated with them. So what is this co-boundary map? So the co-boundary map is basically, you can think of it as a map between the space of real valued function on the ith faces to the space of real valued functions on the I plus 1 faces. So for example, one of the co-boundary maps is a map between the space of real valued functions on the vertices and the space of real valued functions on the edges. And similarly for edges to triangles, triangles to k-4s, etc. And so the way I'm defining it here, it's maybe a bit unintuitive, but it's the most convenient to work with, essentially. So I'm giving you a matrix description of this operator. So of course, since it's a map between the I plus 1 face space to the the space of real valued functions on the I faces, you can describe this matrix by denoting the rows as basically the canonical or indicator functions on the I faces, and the columns, the I faces, and the rows, the I plus 1 faces, where you can think of the I faces and I plus 1 faces as their indicator functions. So if it's a bit difficult to kind of follow, don't worry much about what exactly it's saying. Just think of it as a matrix whose rows are indexed by the I faces and columns are indexed by the columns are indexed by the I faces, rows are indexed by the I plus 1 faces, and each entry is given by this formula. And this formula is defined in terms of the sign operator I just defined. So it's a 0 ± 1 matrix always. So maybe we should look at a concrete example. We'll do that in a couple of slides. But here's another quick definition, is that once you have the co-boundary operator, you can define its algebraic adjoint, which we denote by the partial sign, and we call this the boundary operator. So it goes from the, let's say, edges to the vertices or triangles to the edges. It goes in the other direction. So as you can see here, this diagram kind of shows you where these maps are going. So for example, if I is 0, that means I have a map. So delta I would be a map from the space of functions on the vertices to the space of functions on the edges. And the deltas go in the other direction. So here's a concrete example. So here's the same graph I showed you earlier with this particular ordering. So delta 0 is a matrix whose columns are indexed by the vertices and the rows are indexed by the edges. And the entry at any given position can be computed by the sign notation I introduced earlier. And these are concrete examples. For example, the delta 1 is a map between the edge space and the triangle space. So since there are two triangles, there are two rows. Yeah. Any questions so far? Anything?
Okay. How is the +1 -1 determined?
That is determined, okay, by this notation. So for example, let's look at this entry, the entry at the intersection of 1, 2 and 1, 2, 3. So I can get from 1, 2 to 1, 2, 3 by adding the element 3. But if I add the element 3, and I order the 3 elements 1, 2, 3, it's sitting in the position 2, right? 0, 1, 2. So it's an even number. So yeah. So if I go back one more slide, sorry to go back and forth, but basically, if you order the elements, you need to look at what position is the extra element sitting at. And that tells you whether it's +1 or -1. So I should probably mention this. A lot of these things, we care about this science because we're doing things over R, but a parallel kind of theory can be developed over F2, where people don't care about science, particularly people who do like a topological data analysis. They do things over F2. For us, we're doing over R. It can be done over Z, etc. Yeah. Okay. So now here's the main kind of operators that are of interest to us. Is this upper Laplacian, which is the composition of the delta I and delta I transpose. So you go from let's say the edge space to the triangle space, then you come back to the triangle space. Or you start from the triangle space, you go to the K4 space, and then you come back. And the lower Laplacian is defined analogously. So you first go down and then come back up. And the total Laplacian is just the sum of these two operators. So yeah, so basically, each of these operators that I've defined is an operator on the space of real-valued functions on the ith space. So they're not going anywhere else. It's on the same space. So here, the same graph that I introduced before. So the co-boundary operators I've showed earlier. If you calculate these objects, you get these two matrices, which is the upper and lower Laplacians at level 1. And you can do it at each level. So yeah. So
at level 1, would that be the total Laplacian? Is that the same as the Laplacian?
That is true for level 0. I was going to go there. Yeah, but level 1 is not. Yeah. Yeah. So as you can probably see already here, that these matrices are kind of nice. They're symmetric. They're each row have the same number of 1s and -1s, and the diagonal entries are all the same. So not surprising that these are like they're specifically examples of gram matrix. So real symmetric matrices of the form A transpose times A. So they're like diagonalizable. They have a full set of orthonormal eigenvalues, eigenvectors, and then their eigenvalues are all non-negative, etc. So there are nice matrices to study the eigenvalues of. And here I've kind of listed the eigenvalues, as you can see. The first row gives you the eigenvalues. The second rows are their multiplicities. And as you can see, all the eigenvalues are, in this case, integers. And the rows, they're all non-negative. And the integers are not very, it's not a coincidence. Yeah, there are a bunch of papers that kind of describes for what graphs you get these integer eigenvalues, which is like a completely separate direction that I'm going for today. But the eigenvalues being integers is not a coincidence. Okay, so here's some basic properties of this operator. So if you take any two of these co-boundary operators I defined and compose them, back to back, you get the zero operator. So in terms of these algebraic terms, it's going to create this chain components. So the image of each operator is contained in the kernel of the next. So in particular, later in the talk, I'll be talking about some sufficiency conditions on the graph that makes this chain complex exact at certain positions. But the property one is basically telling us that this is a chain complex. And of course, if you compose the two upper or lower operations at the same level, you also get zero, immediate consequence of level one. And the reason this is important is that it allows you to kind of decompose the eigenspaces nicely. So in other words, if you take the upper Laplacian, lower Laplacian, and the total Laplacian, and if you can get a handle on any of the one eigenvalues for any one of these operators, you get the eigenvalues for the remaining ones. So this is why this orthogonality property is important. And there are some other properties that I've listed. There's a very elementary kind of linear algebra facts that are consequences of these matrices being Gram matrices. I'm not going to go into any of the details here, but just know that there's a lot of structure. And kind of the canonical big result on these matrices is called the discretized Hodge decomposition. So it decomposes any of these spaces into like 3 orthogonal pieces. It's not one of the big results. We're not going to need that, but I thought I should mention it. It's called the discretized Hodge decomposition. Okay, so first non-trivial thing that, not non-trivial, but things related to what we are working on, basically. So if you take the first matrix that I just defined, L0 up, that turns out to be the usual graph Laplacian. That is one of the most like studied object in spectral graph theory. And that is important because that matrix basically captures a lot of information. For example, number of connected components. For regular graphs, the Laplacian gives you the second largest eigenvalue of the Laplacian gives you an upper bound or lower bound. Sorry, I can't remember, but it's related to the diameter of the graph. So graph Laplacian is very important. And if you take the first matrix that I just defined in the sequence of all matrices, the first one is the Laplacian. So the next ones that I'll be talking about, particularly exactly the next one, L1 up, that basically hopefully contains a bit more information than the Laplacian or different kinds of information. That's the hope. So before I go into our work, I just wanted to mention a couple more papers that study these same objects, but on different simplicial complexes, not necessarily Clique complexes of graphs. For example, there's this paper by Alan Liu from 2020. He establishes this relation between the size of the maximal missing phase in a simplicial complex, meaning it's a set that's not in your collection, but all of its subsets are in your collection. And there's a relation between the size of that maximal size missing phase, and the kth largest or smallest, rather, eigenvalue of this Laplacian operator I just defined. And here's another paper, which is a lot longer, this spectral gaps of generalized flat complexes. He has a bunch more results of that sort. So people have been studying the eigenvalues of these operators that I've defined to study the combinatorics of the simplicial complexes for some time. And we took a different path into this, but there are like other groups that have been studying the same objects. So for us in particular, of interest are Clique complexes obtained from strongly regular graphs. The reason we looked at these graphs is because for general graphs, the problem is too difficult. So you want some sort of regularity in your graph. In fact, the more regularity you can have in your graph, the more structure you have in your graph, the easier it is to study the Clique complex. So we took the kind of the sweet spot of regularity and hardness of graphs, which is strongly regular graphs. So a quick definition: a strongly regular graph with parameters vk, lambda, mu is just a graph that has v vertices, is k-regular, and for any given pair of adjacent vertices, there are precisely lambda common neighbors. and any pair of non-adjacent vertices, there are mu common neighbors. So these are called strongly regular graphs. And it turns out that if you take the complement of a strongly regular graph, its complement is also strongly regular with these parameters. So the reason, okay, a couple examples first. Here's the Peterson graph. Probably everybody has seen it. It's a strong regular graph on 10 vertices, degree 3 regular, lambda 0. So no pair of adjacent vertices have any common neighbor. In other words, there's no triangles. And mu equals to 1. So if you take any pair of non-adjacent vertices, they have exactly one shared neighbor. And here's a whole class of strong regular graphs. So these are called triangular graphs, which we have studied, and I'll give you some results on it. So the vertex set of this graph, of the graph Tn, is all pairs of symbols from 1 through n. So 1, 2, 1, 3, 2, 3, etc. And two of these vertices are adjacent if and only if they share exactly one symbol. So here I've showed you T4. So as you can see, the vertex set is 1, 2, 1, 3, 1, 4, 2, 3, 3, 4, 2, 3, etc. I think there's a typo. This should be 2, 3. And two of them share an edge if and only if they share a symbol. And it turns out that these triangular graphs are actually, each of them is a strong regular graph with these parameters. So n choose 2 is easily seen to be the number of vertices because there's that many pairs. And it's an easy exercise to show that these are the parameters for the strong regular graph.
And is it always pairs? The vertex set is pairs of
Yes.
numbers from 1 to n?
Yes, it's just n symbols. It doesn't have to
N
be
choose 2.
n choose 2. Yes, that's the triangular graph T sub n. Okay, so the reason strong regular graphs are well studied in the spectral graph theory area is because their eigenvalues are very nicely related to their parameters, regardless of their actual structure inside. So if you have a strong regular graph with parameters vk lambda mu, where we're eliminating the complete graphs or unions of complete graphs. So all the basically edge cases, if it's not a complete graph or it's complement or a union of disjoint complete graphs, then its eigenvalue, it always has exactly 3 eigenvalues. The largest eigenvalue is the regular degree with multiplicity 1, and the 2 other eigenvalues are this, that can be directly computed from their parameters. And we also know their multiplicities, which is also something that can be directly derived from the parameters. So strong regular graphs parameters determine their eigenvalues. But it's not true that the eigenvalues determine the graph structure. So there are many pairs of strong regular graphs with the same parameters, hence the same eigenvalues, but not the same structure. So here's the first question we ask. If the adjacency spectrum of the eigenvalues cannot determine the graph structure, is it possible that the L1 up, the additional structure that we just defined, the incidence between edges and triangles, maybe that can determine all the strong regular graphs? Because in spectral graph theory, it's an important problem to study what graphs are determined by their spectrum and what graphs have, we call them cospectral mates, basically different structure graph, but with the same eigenvalues. So it turns out that, here's a concrete example. So it's a theorem from the 50s that if you take the class of strong regular graphs for each n, they are always determined by their spectrum, except for the case n equals to 8. Meaning, if you take the strong regular graph Tn for n not equal to 8, there are no other graphs that have the same eigenvalues as this graph, except for the t equals to 8 case. And for t equals to 8 case, there are 3 graphs, non-isomorphic graphs. We call them Chang 1, 2, and 3 graphs. And here they're L1 up spectrum. So the operator I just defined, if you look at their spectrum, it easily can see that these are different. So here's the first kind of class of strong regular graphs for which the usual Laplacian, usual adjacency spectrum wasn't enough to distinguish them. But when you look at the spectrum of the operator I just defined, they are distinguished by that spectrum. So that kind of gives you the motivation of our our study that okay, these things do have sometimes more distinguishing power. So maybe there's something to study here. So yes.
What happens at n equals 8? So how is it different from the
So you can actually like compute two different graphs. And the reason n equals to 8, well, so I don't remember the exact proof, but it's a theorem like that's like 1 page long, where basically you can show that except for n equals to 8. So basically in the theorem, you show that when n greater than 8, so at least 9, you have enough vertices to kind of get an isomorphism. And for n less than 8, we kind of manually check that these are the only ones. But for n equals to 8, that's the kind of one case where you don't have enough vertices to kind of force things. And also like there's some freedom to kind of construct different things. But yeah, I mean, I can't really say more than that on this. Basically, yeah, if you have too many vertices, it kind of forces some structure. That's all I can say. Yeah. But if you're interested, it's like a just 1 page theorem in Van Linden Wilson's textbook. Yeah. It's actually very elementary. Yeah. Any other questions? Okay. So here's some other kind of oh yeah. So once we saw that, we thought, okay, maybe L1 up spectrum is kind of enough to distinguish all pairs of strongly regular graphs, but it's not the case necessarily. Which so it's not completely enough. I'll get to more on that later. But here's some more examples where there are many graphs, many pairs of graphs with the same parameters. So they have the same adjacency spectrum, but their L1 up spectrum are distinct. So there are more examples why L1 up spectrum might be useful. Here's some more examples. I'm going to skip them. So that was kind of the motivation for us to study these higher level spectrums, Laplacian spectrums. So here's some lemmas we found and lemmas from other places. And I want to kind of give an idea of how we use these lemmas to kind of compute these spectrums for some classes of graphs. So the spectrum of the Laplacian operator of the Clique complexes of certain classes of strong regular graphs. So here's a quick lemma that is not our lemma. This is kind of one of the earliest like computations. Was probably also the easiest case, I would say, because it's a complete simplicial complex. You have all sets of up to certain size. So for here, I'm saying Kn, so you have all of them. But yeah, it doesn't hard to delete some of upper level stuff. So for this Laplacian operators, Li up at any I, you can find the eigenvalues. And there's just two eigenvalues, 0 and n, and also know their spectrum, multiplicities. Not too interesting. This is something we did now, the Hamming graphs. So the Hamming graph H and Q is a graph, a strongly regular graph, which whose vertex set is all couples of length n, and whose entries are coming from a alphabet of size q. And two vertices are adjacent if and only if they differ at exactly one coordinate. And it's easy to show that these are strong regular graphs as well. And this is our kind of first result, which is an easy exercise, but this is kind of the one of the like basically first kind of like computation that we did, and we couldn't find any other computation anywhere other than the complete one. So you can compute the L1 up spectrum of this Clique complex of these graphs, and this is shown on the slide here. And I've only listed L1 up, but we've computed the other levels as well. We're particularly interested in the next level, so L1, so that's why I'm listing them, but we have done the other computation as well.
And L1 is number of edges in triangles.
This L1 up is a matrix, yes. So the row and column number would be the number of edges, yes. So this is another lemma we found that if your graph has a structure that, actually the simplicial complex has a structure that each I phase is exactly in one I plus one phase, then the spectrum at Li up spectrum can be computed easily. And if we apply this to this point graph of a generalized quadrangle, which I'm going to define in a second, we get their eigenvalues as well. So a generalized quadrangle, GQ of k minus 1 and r minus 1, is an incidence structure, basically. So it has it's an incidence between points and lines, and any point has any line has k points, and any point has exactly r lines going through it, and 2 points distinguish a line. And anytime you have a point that is not on a line, there's exactly one line going through that point and some other point on that line. So you can create a strongly regular graph, which is a point graph of this generalized quadrangle. And the way you do it is that you just take the points in your incidence structure as the vertices and put an end edge between two vertices, if and only if they share a line. And again, it's not a very hard exercise, although it requires a little bit of work to show that such graphs are also always strongly regular graphs. If I apply the previous lemma I just mentioned to this point graph of a generalized quadrangle, we can immediately get the spectrum L sub S up spectrum at level S, and it also has only two different eigenvalues with these multiplicities. And they all kind of boil down to this regular structure these graphs have. So basically, there are some large cliques that don't share much, if that makes sense. So these are kind of some easy computations we did. Yeah, but this is this theorem 1 here, was the first hard theorem. So if you think about the triangular graph I just defined a few minutes back, and if you look at their L1 up spectrum, it turns out that they always have 5 eigenvalues for n at least equals to 4. For n less than or equal to 3, there are more eigenvalues. So if you have these n at least equal to 4 and look at the Clique complex of these triangular graphs, they always have these 5 eigenvalues, and they have these predictable multiplicities as well. In fact, we proved more. We actually constructed descriptions of, or constructed or gave descriptions, rather combinatorial descriptions of the complete eigenbasis. So all the eigenvectors belonging to the eigenvalues, except for these n minus 1 eigenvalues, for which we do not really have the description of the eigenvectors. But this eigenvalue was found by first finding the remaining ones and then applying Cauchy-Schwarz to say, okay, there must be a single eigenvalue, and that must be n minus 1. But for the remaining ones, we found exact description of the eigenvectors. And this turned out to be very not easy at all. It required quite a bit of work, especially the proof. Even if once you realize how the eigenvectors are going to look like, it requires quite a bit of work to kind of argue this. So that kind of motivates us to kind of try and develop more standardized methods to find eigenvectors and eigenvalues of these higher level spectrums, higher level Laplacians, like the way we have for the usual adjacency matrix for graphs. And I'll actually come back to that, and I'll mention it as one of the things that might be worth working on later. Yes.
So these spectrums are not determined in a graph, right?
So no.
That's one of your goals, but not getting there.
Yeah. So this is kind of going in a sideways direction where we're trying to kind of develop some tools and computational facts to study different classes of strong regular graphs. Yes. So I'm not going to kind of give you any description because the descriptions are, although combinatorial, is kind of not very illuminating, I would say. Like if you had a computer, you can sit down and actually find them, those eigenvalues. But yeah. So the higher level spectrum for these graphs are kind of easy to do. Like L2 up requires a little bit of work, and starting from 3, these are completely a kind of obvious. They kind of group in these nice blocks, and they can be immediately computed. So L1 up is where you can potentially find some extra information, I'd say. So there's another kind of results we kind of found. So to give you a little background, so when we're studying all these different kinds of strong regular graphs, it turns out that many of the strong regular graph classes that we have studied happens to have, at least computationally speaking, when you're looking at the computations, have the property that the image of the delta zero, the map from the vertex space to the edge space, that is exactly equal to the kernel of the map from the edge space to the triangle space. In other words, this I don't have to write down, but if you think about the chain complex I mentioned, 0 to the space of functions on the vertices to the space of functions on the edges, this graph has the property that that chain complex is exact at the vertex level. And so in other words, it also gives you the dimension of the zero eigenspace, because for a connected graph, it's a result from the Biggs that the Biggs textbook. It's a very old result that for a connected graph, the dimension of the image of delta zero is number of vertices minus 1. In general, it's going to be number of vertices minus the number of connected components. So if we can find some sufficient conditions for the graph to be exact at that level, at the vertex level, which is the same as saying the image of delta zero is kernel delta one, that immediately gives us the dimension of the eigenspace, zero eigenspace. So we did find a number of kind of sufficient conditions for that as well. And so here's kind of the main kind of result that theorem 2, even though it doesn't look very useful here. So it basically says that if your graph has the property that if you have any induced cycle, then it always has 4 consecutive vertices somewhere on that cycle that share a vertex as a neighbor. Then your graph will have this property. And the proof idea is basically this. Like if you look at the quotient graph, quotient group, or you can think of it as a module. Actually, it's a quotient vector space in this case because we're doing things over R, which is a kernel delta 1 over image delta 0. I'm trying to show that this is trivial, which is equivalent to showing that kernel delta 0 transpose over image delta 1 transpose is trivial. So it's a map that comes from like vertex to the empty set versus edge to vertex divided by the map that's coming from triangle to edges. That is trivial. So that way, so for all of this mostly, we worked on the right-hand side, not the left-hand side here. And for that, we basically showed that, okay, if you have a cycle essentially in the graph, which is kind of equivalent to the kernel elements in the delta 1 transpose, they can always be kind of triangulated. I'm not going into any of the details here, but the basic idea was cycles can be triangulated in the graph. And then you just have to check that the signs match up and the cycles basically generate the whole kernel space, etc. So the fact that the cycles generate the whole kernel space is also an old result from Biggs. And the cycles can be triangulated is a consequence of this property that we're taking as an hypothesis. And in this form, it doesn't look very useful, but here's an example, like a corollary basically that you can. Yes.
So is triangulated equivalent to that property, the 4 consecutive of a common vertex?
It's not an equivalence condition, but it's a consequence.
The triangulation follows from that.
Yes, triangulation will follow from that common neighborhood property. And so if we take that result and apply it to strongly regular graphs, then we get this nice linear inequality among the parameters of the strongly regular graph. And note that it doesn't have the V parameter as well. It's a linear inequality between only 3 of the parameters. Then it forces this graph to have this property, which is the same as saying this, the one cohomology group is trivial in that chain complex. And the proof outline, I could probably do it on the board. How are we doing on the time? Is it clock? 12:43.
10 minutes.
Okay, in that case, I'm going to skip that. But if we have time or interest, I can come back to it after we end. So once we have those kind of tools and techniques, we can immediately apply them with some creativity with different other classes of graphs. For example, I'm going to give you 3 different classes of graphs for which for all sufficiently large members of these classes have the trivial one cohomology group. So the first one is a Kniza graph Kn2. It's just the complement of the triangular graph Tn. So the same vertex set, all pairs of symbols on the set 1 through n, and 2 pairs share an edge, even only if they share no symbol at all. And it turns out that it's a strong regular graph with these parameters that I've listed, and you can show using the techniques that we have developed that all these graphs, or sufficiently large graphs of this collection, will have a trivial one cohomology group because all the cycles can essentially be triangulated. And for the Paley graph, so a Paley graph is of particularly interest because they have this kind of universal property. I don't think I have time to go into that, but Paley graphs is an important class of examples for spectral graph theory. So it turns out that for Paley graphs, the requirement that all sufficiently large Paley graphs have the property that any 4 vertices have a common neighbor is automatically satisfied. And we didn't have to do much here. We just applied the previous theorem. And the other class of graphs, we have this Latin square graph. So a Latin square of order n is just a matrix with entries from 1 through n, such that in each row and each column, each symbol appears exactly once. And given a Latin square, you can create a strongly regular graphs out of it, where the vertex set would be just the coordinate positions, and 2 coordinate positions would be adjacent, if and only if either they're on the same row or in the same column or have the same symbol. And you can show that it's also a strong regular graph with these properties. And this one required a bit more work, but it can still show that all sufficiently large Latin square graphs would also have a trivial one cohomology group. So these are the 2 kinds of results we have. And I want to finish by telling you a little bit more of what do we think are worthwhile to study in that field. So first of all, the L1 up spectrum, you can deduce certain parameters. For example, the lambda parameter can be obtained from it. Product of V and K parameters can be also obtained from it. But what other graph properties are determined by the L1 up spectrum, in particular for strong regular graphs? Is it true that they always contain at least as much information as the L0 up, which is the isograph Laplacian? We don't know. Also, if you have 2 strong regular graphs and they're the same L1 up spectrum, they have the same L1 up spectrum, what can you put in there more to make the 2 graphs isomorphic? Like what is sufficient alongside the L1 up spectrum to make 2 strong regular graphs isomorphic? And also the second kind of result I just showed you, the sufficient conditions for one trivial cohomology group. I'd like to find some necessary and sufficient conditions. And also, let's see, what else is there? Strong regular graph. Oh yeah, I would very much like to develop some more general techniques to compute these L1 up spectrums, because we have many techniques to do it for the like L0 up spectrum, which is the usual Laplacian, but we don't have much on the higher levels. So I'd like to develop some more. And let's see. Oh yeah, this is another question, the last one. That was kind of asked by Nikhil Srivastava when my advisor was visiting Berkeley last summer. So he asked basically, okay, this L1 up spectrum, like how fast the number of distinct eigenvalues can increase with the order or the size of the graph. And there are certain classes, for example, the triangular graphs, as we saw, it only has 5, right? It doesn't have many distinct eigenvalues. On the other hand, if you compute some of the Paley graph examples, they turn to have like many different eigenvalues. But we don't have any actual like a theoretical result to argue that how fast it grows. So we'd like to also understand this a little bit. And one way to study this would probably be studying the characteristic polynomial of the graph, which is basically giving you the L1 up matrix. So that matrix, if you ignore the diagonal entries, can be viewed as the matrix of a signed graph, right? So I think there's something to study there. I haven't made any progress in that direction, but yeah. So that's basically kind of concludes my talk. And if there are any questions, please go ahead. Yeah.
I have one.
Sure.
You kept saying L1 up, but there were
Yes.
no results about L1 down.
Yes, so it's not a surprise because as I said before, like if you know the eigenvalues of L1 up, you can get the eigenvalues of L1 down, and you can get the eigenvalues of the total Laplacian, and vice versa. So I just chose one, and I've been talking about that, but they're all equivalent. Yes.
Now, it's strongly, so in the hierarchy of graph classes, you have regular graphs that really just calls the complexity of
Yes.
like all graphs for
Yeah.
some reason. And within them, you have strongly irregular graphs that is also very
Yeah.
complex.
Yeah.
Do you think you would be able to find something that distinguishes them by way toward isomorphism, as you had said? That seems like a really hard problem.
If I understood your problem correctly, I think that is something I already alluded to, right? Like,
Yeah.
what more do you need alongside the
Yeah.
L1 up spectrum to force isomorphism, right? My intention is that it's actually a very difficult problem, but that is something we're kind of thinking about. Yes, like what exactly can you tell from the L1 up spectrum or like L1 down spectrum? Like how much are you getting from it? So maybe I should mention this one thing that I forgot to mention that's relevant. So we found examples of strong regular graphs which are not determined by their spectrum, but are determined by L1 up spectrum. We also have examples of graphs which are not determined by their L1 up spectrum either. What we don't have is any pair of graphs which fail to be distinguished by their L1 up spectrum and the L1 up spectrum of their complement. So it's possible that the L1 up spectrum of the graph and its complement is sufficient to distinguish strong regular graphs, but we don't know. Like that's just a thought. Yeah. Yeah. Any other question? Yes.
You mentioned that L0 is the usual Laplacian.
L0 up.
And, so up.
Yeah.
And I guess so Li up is a generalization of that, right?
Yeah,
so,
you can think of it. Yeah.
So right. So I was wondering, I mean, you have like you generalize something, a different way to generalize, and so on. So why this way of generalizing? Maybe there's another way of generalizing which is more useful or different. I mean, so what? So is there any intuition of why you choose this particular way of generalizing L0 rather than
Yes,
way?
yes, yeah. I think I kind of alluded to a little bit as well on this either. So basically, if you think about the let's say the adjacency matrix, what is it capturing? It's capturing the how the vertices are kind of included in the edges, right? Incidence structure between vertices and edges. What is L1 doing? It's capturing the incidence between edges and triangles. The delta 0, delta 1 operator. So it's kind of the obvious next step, at least to me, like incidence between edges and triangles. And the next one is going to be the incidence between triangles and K4s. So it's a generalization in that direction.
Right, in adjacency, you don't have the plus or minus one.
Yes, yes. So we're introducing this extra kind of signs. Otherwise, like you don't have a chain complex and you don't have these like nice eigenvalue properties. Yeah. So the signs, okay, maybe this is relevant here. So these signs are not something we invented. These are standard machinery coming from algebraic topology techniques. So basically, when you're studying these boundary co-boundary operators in algebraic topology, these signs are very natural. They're required to make things work. And they just got carried over to the combinatorial version of simplicial complex. So now you may say, okay, what if we eliminate the signs? Well, you can get some nice regular graphs, and maybe there's something to study there, but that is not something we have done. Yeah.
One can maybe wonder about this generalization. Except for L2 and F, it's easy to calculate. It becomes
not always for the triangular graphs.
not always.
Yeah,
Okay.
not always. No.
Okay, good.
Yeah.
No, I think that's not a good definition.
Oh, no.
In general, it can be.
Yeah, in general, like many classes of graphs, especially it gets super tricky, like later. Yeah. Any other questions? Is there any questions on Zoom maybe? No, I don't see anything. Okay, I think that's it.
Let's thank the speaker.
Thank you.
Close the recording.
Yeah.
Thank you.
Thank
That's
you.
very nice.